Hi class, I want to first talk about Ohm's law and also add a little discussion on Kerckhoff's current laws and Kerckhoff's voltage law. Ohm's law, if I were to ask what Ohm's law was, and you'll probably say V equals IR, where the voltage equals the current times the resistance. Now this is good to know, but it's often students use this incorrectly because they don't remember that it should be delta V equals IR, or the voltage drop across the resistance is equal to the current times the resistance, such that V1 minus V2 is equal to IR. And the reason we say V1 first minus V2 is because if current is really going from right to left, from left to right in this direction, then V1 must be a higher voltage than V2 in order to drive that current. Another way to think of this is with fluids. If you have some pipe with some sort of build-up resistance, any model resistance or energy loss, if the pressure is the same on both sides, then you're not going to get any current flow or any water to flow across the pipe. But as soon as pressure on one side is greater than pressure on the other side, then you will get current to start flowing. Therefore, we need to always remember that it's delta V equals IR and not just the voltage V equals IR. This often is a problem for students when I give them a circuit that looks something like this. If I give you a couple resistors, let's say, going to ground, and let's say you happen to know this voltage here is V1, and I say, what's the current through this resistor R1? Well, students again will say, all right, current equals voltage over resistance, so I1 is equal to V1 over R1. Well, that's not correct, because remember, it needs to be a delta V, which means this V1 needs to be V1 minus something. If it's going to be minus 0, then the resistance is going to be, it needs to include both resistors in series. So it really should be R1 plus R2. Or, if you knew this voltage right here, V2, you could say I1 is V1 minus V2 over just R1. So again, be careful with how you use Ohm's law. Okay, so now I want to talk about Kerckhoff's current law. Kerckhoff's current law, or we sometimes just call it KCL, means any currents going into a node have to equal all the currents coming out of a node. Therefore, I1 plus I2 have to equal I3 and I4. So another way to think of this is if you have a network of pipes, all the water coming in to a joint has to equal all the water coming out. We're not creating or losing any water. Okay. We can use this in addition to Ohm's law by remembering that I equals delta V over R to, instead of just relating currents, we can also relate voltages. For example, let's say we replace each of these currents with actual, there's a resistor, and we actually have the voltage on each side of that, on those resistors, and the voltage in the middle we're just going to call Vn. So let's say we're tasked with finding the voltage Vn. Well, we can take each current in our Kerckhoff's current law equation and replace it with an equivalent Ohm's law. For example, I1 is, because current is going from left to right, we know that V1 has to be greater than Vn. So we're going to say the delta V is V1 minus Vn over R1. And similarly with I2, I2 is V2 minus Vn over R2. And I3, that's because now current is going out of the node, Vn must be greater than V3, so we're going to now have Vn minus V3 over R3. And similarly with I4, Vn minus V4 over R4. And we can use these four equations and plug them into our Kerckhoff's current law equation. Well, we can do that really quickly here, all in one step. We can say, well, the current's coming in, I1's going in, and I1 is V1 minus Vn over R1. I2 we're going to assume is going in, so that's plus V2 minus Vn over R2. And that has to equal the currents coming out, which we assume is I3 and I4, so Vn minus V3 over R3, plus another current coming out, V4, so it's, or I4, so the current I4 is calculated as Vn minus V4 over R4. So now we can take this one equation, if we know our voltages V1, V2, V3, and V4, and our four resistors, R1, R2, and R3, and R4, then we can rearrange it and just solve for Vn. So here's a way we can combine our Kerckhoff's current law with our Ohm's law. So now, to you about Kerckhoff's voltage law, or our KVL equations. So Kerckhoff's voltage law means that if you have, let's say, a voltage source and some network, resistors, or whatever, if you go around a loop, then that sum of voltages have to equal zero. This is similar to thinking of a pressure. Let's say we are here in Rexburg, and we're at some atmospheric pressure. Well, if we go and climb the Teton mountains, then we're going to lose pressure because we're gaining elevation, which is at higher elevation, we have lower pressures, so we're going to lose pressure. And then let's say we climb back down to some, let's say even sea level here. And at sea level, we've now gained a lot of pressure because we're at a lower elevation. And then we get into the ocean and drop down into the ocean. Hopefully you're breathing. We'll gain a lot more pressure. And then we get out of the ocean and fly and head back to Rexburg. Well, if we add up, well, we're going to, again, lose pressure. But if we add up all of these pressure increases and drops, then when we get back to our original location, we shouldn't have changed any net pressure. Same thing with voltage. If we just pick a point and go around a loop, clockwise, counterclockwise, whatever, if we end up back at the same point, then all the voltages have to equal zero. So, let's look at that in a circuit. So let's say we have some voltage source, or let's call it V1, and we are going to go across resistor R1, and let's say we have another voltage source going in the wrong direction for some reason, and another resistor R2, and a third resistor R3. If I could put ground somewhere, all that really means is our ground is some reference point we're going to call zero. So we can just pick somewhere and say, well, this is zero. So it's not specified That's okay to put that there. But it really doesn't matter because any point we pick to start and going around is going to, once we get back to that original location, then our voltage should all sum to 0. So if we start here, and let's say we go in a counterclockwise, or sorry, a clockwise fashion, we should have one current going through all of these. And so we're going to have, if we do assume current is going in that direction, then starting from below this, starting here and going to the left, we're going to run into a resistor. Well, if we made this loop and let's say current is actually going this way, then that means the voltage on this side should be higher than the voltage on this side. So we're going to actually lose voltage. So our first equation will have a minus V due to R3. And then if we come up to here, once we get to our first voltage source, we're going to increase the voltage, V1, and then we'll come across to here, and we're going to, again, hit another resistor. Again, if current is going this way, then the voltage on this side of the resistor must be higher than this side, so we're going to lose some voltage here. Again, coming to this, now at this second source, we're going from the positive side of the source to the negative side, so we should be dropping voltage, so it'll be minus V2. And then if we go through current here again, if current is really going this way, then this side of the resistor has to be a higher voltage than this side, so we're going to be, again, losing voltage through R2. Now that we're back to our original point, then we're going to say that equals 0. So now we have an equation to relate our voltages. We can now use Ohm's law, and remember that a delta V equals IR. If these I's really are the same, then we can say, well, the voltage across R3 should be the same current through all of this loop, and so I'm going to just call it I. So we have this current I going through the loop. So the delta V across this resistor should be IR, or the VR3, or the delta VR3 should be IR3. So I can replace this first term in the equation with minus IR3. And then V1 is our voltage source. R1, again, we're losing voltage, so minus IR1. Then we have our V2, and then our last resistor is IR2 equals 0. Now, with this equation, we can simply rearrange it, and if we know V1, V2, and R1, R2, and R3, we can rearrange it and solve for our current I. So again, I hope you can remember that the sum of voltages around a path, once we get back to the original point, should be equal to 0. Now, if I ever wanted to just know the voltage at a point, so let's say I wanted to know the voltage at this point right here. Well, if I start from a known point and do a Kerckhoff Voltage Law up to that point of interest and stop, I can call that equal to some V that I'm trying to measure, or some V desired. So if we wanted to do that, we can say here, alright, V desired, let's start at this known point and go backwards. So we already assumed I is going down, so if we start here, if I really is going down, and I must be going from a low to a high voltage. So I can say, starting at 0, I'm adding voltage, so whatever voltage drop is at R2, and then I stopped at V desired, so that has to equal V desired. And we know that VR2 is I times R2. So V desired must be IR2. Or we can go the other direction. We can start, change pen colors here so it helps. We can start here and go clockwise and end up at this same point and get us another equation. We could say, starting at 0, if current is really going to the left, then we're decreasing voltage, so we could say minus IR3 plus V1 minus IR1 minus V2. Now we got to our stop point. That has to equal V desired. And so either one of these equations will solve for V desired and tell me what they are. But again, I'll have to first calculate my current, which means calculate your current using this equation here, and then I can plug them into the other two and solve for V desired. I hope this helps a little bit with your understanding of the Kerckhoff's voltage law, as well as your understanding